Alright, we're going to look at using some calculus here to sketch this curve, and then a lot of algebra and pre-calc stuff comes into play when we do this. So we have this function x squared over x squared minus 4, so this is a rational function, and those tend to have vertical, horizontal, and or slant asymptotes. This particular one is going to have vertical asymptotes at plus and minus 2. That's where the denominator equals to 0. There's no factors that cancel out. So vertical asymptotes at negative 2. And then we got to tie in the degree. The top degree is x squared. The bottom degree is x squared. So it's going to be the quotient of the coefficients, which will just be 1. So what we're going to do is we're going to use a little bit of calculus, and we're going to find intervals of increasing, decreasing behavior, and then we'll also use the second derivative to find concavity. And we can either use the first derivative test or the second derivative test to find any sort of extrema, any mins or maxes. So we're going to go ahead and take the first derivative here, and that will tell us two things. It'll allow us to look at intervals of increasing, decreasing behavior, and it also potentially help us locate mins and maxes. Okay, so we'll take the derivative. So it's going to be low, and then the derivative of the top is going to be 2x, and then minus the high function, x squared, and then derivative of low is 2x all over low squared. So we're going to have our first derivative is the x squareds are it's going to end up being a 2x cubed and a minus 2x cubed. So those are going to drop out, so we're left with minus 8x over the denominator squared. Okay, and we're going to look for critical numbers. Critical numbers of a function are numbers of the domain for which the function has a derivative 0 at that point, or it's not differentiable at that point. So that is only going to be x equals 0. That makes the first derivative 0. Plus and minus 2 are not in the domain, so they're not critical numbers, so we don't mess with them. However, when we are testing for increasing, decreasing, and constant, I got to check around the negative 2 and the 2. So what I'm going to do here first is I'm going to check around 0. So I'm going to find f prime of negative 1. So if you look at the first derivative, the bottom's always positive. So we're only looking at the minus 8x, and that's going to determine the side. So if we plug in a negative, we're going to get the first derivative is positive. And then if we look at it over at 1, it's going to be negative. Okay, so 0 is in the domain, and what we have here is we have a max because we change from increasing to decreasing at our critical number 0. We're going to test around negative 2 and 2 just to see what the function's doing. Okay, so we'll just put in those dotted lines to simulate the vertical asymptotes. So f of negative 2 is positive, and f of 2 is negative. Okay, so that gives us our behavior. So we'll come back to that when we actually go ahead and sketch the graph. So we've located our one extrema, and then we found our intervals of increasing and decreasing behavior. Okay, so if I want to find the max, the location of it, I have to go back to the original function and plug in 0. And when I do that, I get 0. Other things we can look for are the x and the y intercepts. So this happens to be a coincidence here, but my the maximum is an x-intercept. Okay, so moving along, we're just going to write that chart again. And there's a lot of different things that we can do. So it doesn't have to be a real specified order, but if we're looking at the first derivative, we want to do the intervals increasing, decreasing, looking for maximums. something that we don't have to do in any particular order, but this is something you would have seen in college algebra, and that's testing for symmetry. So your function is symmetric with the y-axis if f of negative x is equal to f of x. So that, think like a parabola is symmetric with the y-axis. If you're symmetric with the origin, f of negative x will be equal to negative f of x. So think of something like maybe the cubic function as an odd function. So we can use that, and that can kind of help facilitate graphing these things, make it a little bit easier. Okay, so I'm doing that right now. I'm just going to test, and because all my x's are even exponents, this is going to be an even function, which means it's going to be symmetric about the y-axis. Okay, so we say it's an even function. All right. So here we're just going to rewrite our first derivative because we're going to refer to it, because we're now going to look at the second derivative, which is the derivative of the first derivative. And this is going to help us locate concavity. So it's going to be the low function times the derivative of the top, which is just negative 8, minus the high function, which is negative 8. So we're subtracting negative 8x, so we're subtracting a negative, make that a positive, times the derivative of the low, which would be 2x squared minus 4 to the first power, and then times 2x because of the chain rule, all over the denominator squared, which will now be x squared minus 4 to the fourth power. Okay, we're going to go ahead and clean it up to look for where we may have our numerator equal to 0, where we might have changes in concavity. So we pull out the negative 8 and an x squared minus 4 to the first power. So what we have left going on is x squared minus 4 and then minus 2x squared. And that's all over x squared minus 4 to the fourth power. So we're going to move on to the next slide and go ahead and simplify it. What's going to happen is we have 1 to the first power here. That's going to knock out one of those. So you're going to have x squared minus 4 to the third power, x squared, and then minus 2x squared is going to give us a minus x squared. So what you're going to have in the numerator is minus x squared and minus 4. If I think about that as a parabola, if I'm thinking of terms of x-intercepts where this would be equal to 0, it'd look like that. So it doesn't have any x-intercepts, which means the only places where I really need to test for concavity are around the vertical asymptotes. Okay, so we're going to go ahead and rewrite our derivative here. And now we're going to check for concavity. Okay, so we're going to check around plus and minus 2. So that means we just need to pick a number less than negative 2, between negative 2 and 2, and greater than 2, and that'll tell us about the concavity. Okay, if I plug in negative 10 in the second derivative, I'm going to get a positive number. So that means we are concave up from negative infinity to negative 2. If I plug in something like 0 into the second derivative, I get a negative number. That tells me concave down on negative 2 to 2. And then finally, f double prime, and I'll pick a number to the right of 2, like 10. That's greater than 0, so now we have concave up. Okay, so we're going to use all of this information here to graph this thing. Okay, so it's a lot of information. Hopefully you've been writing it down as we've been going along, or working out the problem with us. So let's go ahead and do that. So the first thing I'm going to do is I'm going to put in my vertical asymptotes, and we have a horizontal asymptote as well. So we're just going to put in those asymptotes. So this is something you would have done in college algebra and pre-cal. Okay. and then we'll go ahead and write that formula in so you can see that you do have a tie in the leading coefficients, so x squared over x squared minus 4. Okay, now we said on the left of -2, two things. One, it was increasing, and then 2 was concave up. Now, if I want it to be even more accurate, I'll pick a couple of points to plug into my original function to do that. But that's enough. So we're going to draw it increasing, so we know its end behavior is going to flatten out, and then it's going to approach its vertical asymptote from above, or go up to a positive infinity in terms of end behavior. So here it goes. So increasing and concave up. Okay. Now we can kind of cheat here because I know it's an even function, so it's going to be symmetric over y equals x. Not y equals x, the y-axis, excuse me. So I know that it's going to have this piece on the other side of the y-axis. Okay. And I know that it was concave down and increasing from -2 to 0. We have a maximum at 0, and then decreasing and concave down from 0 to 2. And then again you see that symmetry. And then finally, it is decreasing and concave up from 2 to infinity. Okay? So there's a whole bunch thrown at you. Just takes a little bit of practice. It's all skills that you already know how to do. You know how to take derivatives. You know how to take the second derivative. You've been practicing the first derivative test, the second derivative test, and you know how to find the asymptotes, intercepts, check for even and odd, and so there's a lot out there, and it just takes a little bit of practice.